Alright, welcome back. We want to continue on talking about equivalent force systems. I want to add one little thing to what we've already talked about. So we've talked about this idea that if I've got this structure, some kind of a beam here, and we'll say I've got point O over here, and let's say I've got 1 Newton, and then another meter over I've got another Newton, and then 1 more meter over I've got 1 more Newton, and then out here at the very end, 1 more meter, I've got 1 Newton. So equally spaced 1 meters each. Okay. And we've talked about that I can replace this over here with this, I can move all 4 of these newtons to point O here, 4 newtons, so long as I replace the moment that's caused by these 3 forces. So this guy is 3 meters out, that's 3 newton meters. This one's 2 meters out, that's 2 newton meters. So 3 plus 2 gives me 5, and then 1 more newton meter gives me 6 newton meters. These guys are trying to cause a clockwise rotation of 6 newton meters. And those are the same, right? Those are interchangeable if we call this point O over here. But what we can do is and you'll find problems like this where they'll say replace this force system with a single force acting at some point, or find the location to place a single point acting from, let's say they say try to find it from point O. Right? And so what they're saying then is they're saying, well, we'll do the same thing, sum of forces in the y, that equals, you've got 4 newtons. I've got 4 newtons acting in here. So I'm now going to apply 4 newtons at some unknown distance d to try to cause this same moment that would be caused by these guys. Right? And the way you would find that is you would say, well, you would take the sum of moments about whatever point you're measuring relative to, so I'm measuring relative to point O there, and that's going to equal then the resultant force multiplied by its perpendicular distance, d. Right? And so what I would do is I would add up all my moments caused by this up here about point O. Well, that's, again, that's, you've got 1 Newton at 3 meters, and these are all negative because they're all clockwise, and I've got 1 minus 1 Newton acting at 2 meters, and then I've got 1 Newton acting at 1 meter. And I need to apply a negative sign to this. It just dawns on me because this resultant force is also going to be causing a counterclockwise rotation. So all these are all in the same direction in this case. And so notice what I've got here. I've got essentially I've got 3, I've got 2 more, so I've got 6 newton meters. All right, and then I've got a resultant force here of 4 newtons. So my distance then becomes, and I've got 6 newton meters divided by, that's my net moment here, divided by this resultant force of 4 newtons. And what do I get there? Well, I get I've got 3 halves of a meter. Sorry, you couldn't see that. I got 3 halves of a meter there. So what is that telling us then? All right, we're saying that if I put this at 3 halves of a meter, and I put this 4 Newton force 3 halves of a meter from this end, then this is the same as all of these. These are all interchangeable. These are all equivalent force systems. Now note, this is 3 meters. And I've put this right in the middle, halfway in that 3 meters. Right, so this kind of finishes up equivalent force systems, and that leads us right into a discussion that we call one of the last things we talk about in Chapter 4 is distributed loads. So these are you will see these common throughout statics and several courses. Then after these have a lot of practical applications. So distributed load looks something like this. If I've got some sort of a structure and I apply to it, this is what we often call a rectangular load or just a constant load. Right? And what we might say here is we'll call this W for a distributed load, some function of X, where X is going out. And what we would do is we can say, well, I can take this distributed load and I can replace that. There's an equivalent to that, an equivalent force system to that, where I apply a single resultant force at some X bar location. Now, this is W meaning some function of X. That means this can vary. Here I've drawn it as constant, essentially. This is supposed to be a rectangular load, so this doesn't change. But what do I mean by that can vary? Well, the next most common distributed load you might encounter would be some sort of a triangular load. So something that increases as you go further along in whatever direction. In this case, we'll say X. And here we would say this is some W, some function of X. That would be my distributed load. Now, if you look, as you go further along, you get more and more force out here. So that means that you have more and more force kind of concentrated in this area. So that means if I'm to replace this with a single force, I would replace it with the resultant force out here, but it's going to be further out here at some X bar location because there's more force here than there is at this end. So that resultant force needs to be further along. Basically, you're going to place this resultant force in the center of whatever shape you have here. If this is just a rectangle, then we're just going to place it basically halfway in the middle here. Which, by the way, there's a reason I did this one previously. That's exactly what I did up here. This is basically a rectangular distributed load that I've put along here. 1 Newton every meter. And so I've got a constant 1 Newton every meter for a distance of 3 meters. And what I've done is I said, well, now this one doesn't quite work out because I've applied an extra 1 Newton right there at the very end, in addition to these guys going along here. But what we're going to look at then, what we're going to do, we need to talk about how do I find this X bar value. And this is L8, page 2 of something. How do I find this X bar value? That X bar value is basically going to be the, it ends up being the integral across the length of X times W as a function of X with respect to X divided by the integral with respect to length. This W is a function of X with respect to X. So what does that mean? Steve, it's calculus. What does this mean? Well, let's get this down to something. Essentially, this is the, if you look at it, this is basically the net moment divided by the net force, which is what we did up here. Right? Where did I locate this guy? Well, I took the net moment divided by the net force, and that showed me where it goes. So that's essentially what we're going to do here. If I've got some function of X, like this is a linear function, so it's going to increase as X increases, then I might need to actually perform an integral to do so. So the integral is going to be whatever that function is, multiplied by x, and find that integral across the entire length of which that distributed load goes, divided by, essentially, this is your resultant force as a result of that distributed load. That's the denominator. It's the net force. Now, here's the good news. There are some typical / common shapes of distributed loads that we will encounter, and that is the rectangular load. All right, so this is just some constant, we'll say K, over some length L, and its equivalent the resultant force is going to equal whatever that constant is times length L, and we're going to locate it at L over 2. These are your rectangular load. So anytime you've got a rectangular load, I just need to know what is its intensity essentially, what is its value, what's this constant value, multiplied by the length over which it goes. That gives me the total amount of force that's being applied. And then I just need to know over how long that distributed load is going. I can place this force halfway along, halfway from one end or halfway from the other end, whichever way you need to measure. Let's look at another one that, as I mentioned earlier, the next most common that you'll encounter is a triangular load. So the triangular load, and we could derive this. It's not a hard derivative, it's not a hard integral. Well, let's say we're going from basically 0 up to some constant K. And you go from a 0 intensity all the way up to some K value. It's increasing linearly as you go along, and that's spread out across some length L. Well, if you perform the integral here, what you would find is that the resultant force is going to equal 1/2 K times L, and its location, I always say it's going to be 2/3 the length from the 0 point, or the little end, or 1/3 the length from the thicker end, this being the thick end, this being the 0 end. 2/3 the length from the 0 end, 1/3 the length from the thicker end. That's where we'll locate this force. So notice both of these here. This is just simply the area of this rectangle because it's representing the resultant force, or the integral of this with respect to x. And the same thing here, this triangular load, if I integrate it, or if I just find the area of this triangle, it's the area of a triangle is going to be 1/2 this constant multiplied by the length. That gives me the area of this triangle. The center of this triangle is going to be somewhere right in here. And basically the center of a triangle is 2/3 the length from one end, or 1/3 the length from the other end, just depending on where the thickest part of the triangle is. That's where you're going to locate that force. So what we do here is, whenever you see in a problem one of these distributed loads, your goal is on your free body diagram. A lot of times you're going to concentrate that down to a single force on your free body diagram, and then you need to know where do you locate it because of this concept back here of equivalent force systems. If I'm changing this into something else, I need to find where does that need to then get located. Okay, that's a nice stopping point there. I'm going to start the next video we'll look at an example.